A spring is one of the examples of simple harmonic motion. If we have it on a frictionless surface here, we do see this harmonic motion. We know that our force from our spring is minus kx, and if the spring force is, the spring force is the only one causing acceleration here, we would have gravity and normal canceling each other out and no friction. So that is equal to mass times acceleration. If we substitute our simple harmonic motion equations, x is a cosine omega t, and a is minus a omega squared cosine omega t. So doing some canceling, our a's go away, our cosine omega t's go away, and we see that minus k equals minus m omega squared. Negatives go away. And if we solve for omega, we get square root of k over m. So this tells us that for a given spring constant and mass, we can figure out all the oscillatory properties of the system. Though we would need to know amplitude to figure out other stuff. But you should remember that our omega for a spring is square root of k over m. This also gives us a means of determining spring constants based on measuring the properties of an oscillatory motion. Remember, omega is 2 pi over period. So our period then would be 2 pi over root k over m, which would be 2 pi root m over k. And we'll be using this principle as part of a lab we're going to do when we get there. We'll be measuring the period and then comparing it to the ideal 2 pi times root m over k value. A vertical spring actually follows the same sort of pattern as a horizontal spring. You'd think that with gravity being involved, it might work out differently, but that is not the case. If we look at forces on a vertical spring, say up here at the equilibrium position of the spring, the spring force is 0, so our net force is just minus mg. That's pretty straightforward. Down here, there's a point where the string is stretched to a certain point, and the sum of our forces is going to be 0 because or y I should say, the stretch of the spring is causing an upward force that is equivalent to the downward force of gravity. And then, down at a point here, the sum of the forces is going to be positive, and it's still going to be ky minus mg. We'll call this ky1, call this ky0. Down here, so then we can see that the net force is just going to be ky1 minus mg. Well, from up here, mg is equal to ky0. So the net force is ky1 minus ky0. So it's just a k delta y. So in that sense, the forces we can treat as being the same as the vertical case, except we call this point where our ky equals mg, we call this our new equilibrium position. So for a vertical spring, we call the point where if you just where the mass would be at rest. If you let go of it and put it at this length, the gravitational force and spring force cancel each other out. We call that the equilibrium position for a vertical spring. Right? And from there, the vertical spring functions in the same way as the horizontal spring. Now, if we consider energy, well, in the horizontal case, we just have, our energy, we just have 1/2 kx squared, right? We have, as it compresses, it gets 1/2 kx squared, then it turns into kinetic energy, and then turns back into potential and so forth. We've already kind of talked about that. Now with the vertical spring, again, we can ignore the effects of gravity if we call this the equilibrium position. And I'll demonstrate how we can do that. So here, let's say we set y equals 0 at the equilibrium position of the spring. Okay, and down here is the equilibrium position of the spring with mass. You know, this middle point where ky equals mg. I'll call this point y naught. And at this point, we know ky naught equals mg. Okay. Here, our potential energy is going to be 1/2 k times our delta y squared, which is just y naught squared. And then we're going to have a plus mgh. In this case, our height is negative because our 0, we set our 0 up here, so this is minus mg y naught. Okay. If we pick another point, and it doesn't really matter whether it's above or below, just for simplicity of sign conventions, I'm going to put it below. Down here, our potential energy is 1/2 k y1 squared minus mg y1. Okay, so straightforward so far. But now remember, all that's important, physically speaking, is a change in potential energy. So let's look at a change in potential energy between these two places. Take our 1/2 k y1 squared minus mg y1 minus this. We distribute that negative to get a plus mg y naught. We know at this equilibrium position ky naught equals mg. So we can make that substitution minus ky naught y1 minus 1/2 ky naught squared. We're plugging in ky naught for mg. And these are like terms, so that gives us a plus 1/2 ky naught squared. If we factor out a 1/2 k, this leaves us with y1 squared minus 2 y naught y1 plus y naught squared. This is a perfect square. This is y1 minus y naught squared. And this would be exactly the exactly the spring potential if y naught was equal to our 0. So if we considered y naught to be our 0, this would just be 1/2 k y1 squared. So it's just the distance from equal, and so if we made, this is right here, is our distance from y naught, or the place where ky naught equals mg. So if we call that our 0, then we can just say our change in potential energy from that equilibrium position is just 1/2 k. We can just say it's 1/2 k delta y squared. And the effects of gravity are totally canceled out. And this then is just like this, where our change in potential energy from equilibrium is just 1/2 k delta x squared. So we don't have to worry about the effects of gravity because they're kind of incorporated if we just take this middle position to be the equilibrium position.